welcome to Analysis Chat, a bi-weekly discussion with your lecturers for 220. I'm Dr. Biggs, and here with me is Dr. Kikianti.
Hello.
And Dr. Lay.
Hello.
Dr. Kikianti, you seem to be laughing.
It's not bi-weekly.
Yeah, I guess it's getting to tri-weekly now. Maybe we should...
Bi/try, maybe, like, depending on... depending on
every fortnight or so.
Whenever we like.
Whenever we can get a guest.
Yes.
Speaking of which,
Yes.
This week's special guest is Professor van der Walt.
Hello.
Many of you probably know him from 124. He's quite the expert in analysis, and we will have a chance to hear a little bit more about that towards the end of the podcast.
Thank you for having me.
It's wonderful to have you. Okay, so we're a whole 10 weeks in now, more than 2/3 through the whole course.
Almost there.
Yes, just a theme or two to go. But what have we been doing? Well, in the last few weeks, we've finished off with continuity, right? Carefully building everything up like we're doing in the rest of the course from a foundational level. And we proved two of the big theorems that our students know from first year, which was the extreme value theorem and the intermediate value theorem.
Yeah.
And yeah, I mean, the intermediate value theorem already is so powerful to do some things that we spent quite a lot of effort doing earlier, like proving that square root 2 is a real number.
Yeah.
We had like a 4-page proof to prove that. Once we've built up the theory for the intermediate value theorem, we can do it in 4 lines.
Yes.
And this is classic mathematics. Is once you develop a language nicely and develop a body of work, then some things can be simplified dramatically. Okay, what else can we say about the intermediate value theorem? Well, it's another existence result. Existence results are, as I keep saying, beautiful, fantastic, our favorite results. And well, we can design a few things just from the intermediate value theorem. One of the simplest applications, I think, numerically speaking, is the bisection method, right?
To find roots.
To find roots is we can design now a very simple and stable algorithm to find a solution to a nonlinear equation, right? As long as we know that equation is represented by a continuous function, we have a bigger than and a smaller than on an interval, we can keep chopping that interval in half to narrow down to it.
Yeah.
Doesn't converge very fast, but it's very stable, and we can fully justify it with all the tools we have, right? You build a sequence, you know a solution exists by IVT, you know you can keep on doing this and that you'll converge to that solution.
Talking about bi-weekly and tri-weekly, so we can trisect.
Trisect it. Trisection method.
Okay. What else?
The bisection method is in the study guide, by the way. So if any
Yes.
of our students, you should. It's on the study guide, so you should look at it and think about it and see why the method works for yourself by applying intermediate value theorem.
Yeah.
Yeah.
Another basic thing we can immediately prove from the intermediate value theorem is a simple fixed point theorem, right? If we have a continuous function defined on some interval, well, for argument's sake, 0, 1, and its codomain is also 0, 1, we can use IVT to prove that it has a fixed point.
Yeah.
And this is quite powerful stuff. Again, existence of a fixed point.
Yeah.
And I think there are quite many results that rely on the existence of a fixed point. And many numerical techniques are based on the idea of trying to converge to a fixed point of a certain function.
Yeah, that's absolutely true. One of my master's students a few years ago was working on nonlinear partial differential equations, and the existence proof was essentially just an application of a fixed point theorem. It's a very important tool in analysis and its applications.
Yeah.
Yeah.
So it's just a research field in its own, right?
Just the study of fixed points.
Yeah.
Well, yes, in many
not
generalized
correct, yeah.
spaces and
Yes.
so on. Yeah. So we really dug into the epsilon delta definition in this course. Now, I think quite the nice thing about this definition is it very easily generalizes beyond R, right?
Yeah.
We have our epsilon delta and then we state something in terms of absolute values.
Yes.
And what we're really capturing with the absolute values is an idea of distance.
Yeah.
Well, if we generalize the space, then the absolute value generalizes to a norm.
Yeah.
And so in Rn, we have virtually identically the same definition for continuity. So the same idea applies. And well, they already had a taste in 218.
Yeah, they saw that in 218 for functions from Rn to R.
Yeah.
Some of our students who also take 248, which is the vector valued functions, so from
Yes.
Rn to Rm, they also have seen now the epsilon delta continuity there, which is almost the same, except you just replace absolute value with norm when you need.
Yeah.
In whether the domain or the codomain or something
Yes.
like this. Yeah.
Of course, mathematicians love the business of generalization.
Oh yes, this
So-
is our life.
Well, we also had a discussion with Professor van der Berg about why do we generalize
Yeah.
and the appropriate level at asking a question.
Yeah.
And some of the things about continuity, the appropriate level of asking those questions go beyond spaces where we have a distance. So when we no longer have a distance, then we can't generalize our epsilon delta quite that easily. And then we get a new definition of continuity and, well, a new definition of what's going on in our space. And hopefully some of our students will get there with honest topology when we get rid of distance and just look at, well, what is at the heart of continuity.
Interesting.
Yeah. One of the things that I find very interesting about continuous functions is, and that's one of the reasons why people started formulated the delta epsilon definition, is how counterintuitive they can be.
Oh yeah.
And if you just think of things like space filling curves, right, you wouldn't expect this to happen, that you can take a curve which is like kind of one-dimensional and then fill an entire solid block with it without ever repeating any single point. That's absolutely counterintuitive. It's fantastic.
Yes.
By the way, a little advert for honors topology.
Don't you also have an honors project on this? Don't you offer an honors project on this?
On the space filling curve?
Yeah.
I don't think so.
Maybe
I should.
Maybe you should, yes.
Thank you for the suggestion.
Yeah, no, I think this is frequently something that happens in maths is once we establish some theory around something, then we teach it, and then everybody thinks, oh, it's perfectly natural. When in fact, some of those ideas can be quite crazy. I mean, the introduction of zero and the introduction of the negative numbers, when they came about, they were crazy.
Controversial.
Very controversial. It's only after some millennia, like, oh no, we're all happy with square root 2 is a number. No issue,
No
yeah.
issue here. No one gets drowned.
Yeah, exactly. You know? Chase through a field of beans.
Okay. So, we like asking our why questions. We discussed why sequences. Why functions? Why continuity?
Come on.
Again, it's almost
It's difficult.
unimaginable to think of not having these
It's
things.
difficult to answer.
Well, you see, so why continuity? Well, because lots of things we see around us, I think, behave kind of continuously.
Yes.
But if you want to ask, well, why this very particular, very precise definition? It's precisely because things are so strange,
yeah.
right? So up until the early 19th century, mathematicians, great mathematicians, dealt with functions as if every function was essentially everywhere differentiable,
Yeah.
except for a few sort of pathological points.
Yeah.
But then it turns out that things are far more complicated.
Yes.
Right? Weierstrass came up with this example of a function that's continuous but nowhere differentiable.
Yeah.
I think that's why it's so important to understand this concept at a deep level.
Yes. So that's continuity. Next up, integration.
Yeah.
Again, something we have all seen before.
Yeah.
And again, the philosophy we're going to be applying is to, well, build all the machinery up from a very fundamental level, define very carefully what do we mean by an integral, what do we mean by a function being integrable, and then prove some of our classic results, like the fact that every continuous function is going to be integrable.
Yeah.
And of course, once again, we're going to be heavily relying on the infimum, supremum.
Yeah.
We warned you, this is
We
going to
warned
be
you.
everywhere in this course.
We warned you from the start.
At least they don't have lim sub and lim inf.
At some point they will encounter
Yeah.
us, I think.
And I mean, we'll even get a nice, beautiful bonus, like the fact that every monotone function
Are integrable.
is integrable,
Yeah.
right? Even though it doesn't need to be continuous. It could have infinitely many discontinuities, and yet it still is integrable within the very rigid definition that we will introduce. So why integration?
Why integration?
Because it's a fundamental tool that we've
Yeah,
been using
that's it,
from
using-
first year.
I think this comes from the feeling whenever you walk to a restaurant, you see how big it is, and you need to know the area of it.
Yeah. So certainly it has applications in various geometric shapes, asking the question of volume and area.
Yeah.
Well, I think at the heart of it, the definite integral tells you about the total change in a quantity.
Yes.
That's
Yeah.
basically what the fundamental theorem of calculus is telling you.
Yeah.
Yeah, and I mean that's kind of where its origins was with Newton and Leibniz, and Newton was doing a lot of mechanics and looking
Yes.
at
Yeah.
dynamical systems and how they change, right? And you can easily express maybe its velocity, and from that information, how do you get back to its position?
Yeah.
You integrate.
Yeah.
So that is, I think, probably one of its big applications is differential equations.
Absolutely.
Yeah, it's a pity that in this course we didn't get to cover differentiability, derivatives in that sense. So we didn't actually get to talk about fundamental theorem of calculus, which I
Yes.
think is
Astounding.
yeah, of course. Like these two seemingly unrelated things
Yeah.
are actually not related.
Should have sent him to my 1 to 4 lecture last week.
Yeah. Oh,
The
yes.
theorem.
Well,
There you go.
Well, they were there last year.
We also do a wave handing of it in 114,
Yeah.
where we have a reasonable level of
Yeah. I
of
feel like
looking at
it's a bit
differentiability.
incomplete when you talk about integral, but you don't discuss about antiderivative.
Yeah.
But it's okay.
Yes.
Yeah. Here
Okay.
we sort of in this course we cover integral more probably from the sense of well, assuming you have some non-negative function, then you're looking at area under the curve.
Yeah.
You
Or
look,
props,
at,
yeah.
you look at construction of the integral more than
Yes, correct.
Yeah.
Yeah,
Deep down
more than this.
Yeah, I mean, it's
not
more
too
about
calculus. Yeah.
how do we put this idea on a firm setting,
Yes,
solid foundation?
Yes.
How do we introduce the integrability, and how do we show the basic idea like continuous functions are integrable?
Yes.
But yes, I agree. It's a shame we can't push it to that next level
Yes.
of proving with no doubt that yes, the fundamental theorem of calculus holds
Yeah.
from a fundamental level.
Yeah. So
So,
in first year they saw Riemann integral.
well, we kind of talked about left integrals,
Yeah.
right integrals, in terms of left Riemann sum, right Riemann sum,
For monotone functions.
right, and a general Riemann sum.
Yeah.
No, we
This is
introduced the
general.
idea of a general Riemann sum,
Right.
and then we say that it's integrable when all of those general Riemann sums all converge to the same value. Which captures the idea, but it leaves a lot to be desired. Right? It is in essence equivalent to what we're going to be doing here.
Yeah.
But now we're going to be much more careful
Yeah.
with that. So yes, we are going to introduce a very specific idea of integrability, and that is the Riemann integral, which is it's the appropriate level and the first good solid definition we have for an integral.
Yeah.
But of course, it has some limitations, and perhaps it has some advantages too.
Yeah, I think that whenever we're gonna do next, completeness axiom is very important, right? We lose that one, it's on thing vanishes.
Yeah. We can't do it without supremum and infimum. Yeah.
So totally, if you have order in the field but without completeness, so the whole thing doesn't make any sense in
Yeah.
Riemann sum.
Yeah.
Yes.
Yeah. Exactly. Yeah.
Yeah.
Well, I think the Riemann integral is sufficient for just about everything we do at undergraduate level.
Yeah.
Right? It's only when you
Or
When you-
practically speaking. I mean, if you're an experimental physicist, or if you're an engineer, I think most people only use Riemann integral, right?
well, yes, for those people.
Yes, that's what I'm saying. Yeah. Or not.
Well, no. If you look at the theory of partial differential equations, which some of you will become acquainted with in your third year, there you start having to deal with discontinuous solutions of differential equations, and those discontinuities can occur on sets that are so large that the function is no longer Riemann integrable.
Aha.
So maybe they have to go slightly beyond.
So yes, I agree.
Yeah.
For a physicist, for a physicist, everything is differentiable anyway. So
Yeah.
I'm only joking.
Yeah.
Don't offend our physics students.
No, I won't.
So, who was this guy, Riemann?
Who is this guy?
Like, we've been hearing his name for 2 years now.
He has so many names, by the way. Speaking of Riemann.
What? George
Georg. No, it's
Friedrich-
Georg. Georg Friedrich
Georg.
Bernard Riemann. Sorry, I don't really speak German.
Yeah.
But that's, I think, is the best I could. Yeah, so he's German, student of Gauss, is that right?
Yeah,
Yeah. Yeah.
indeed. Yeah, no, and I mean, he made contributions to several areas.
Yeah. In particular, yours.
In particular, differential geometry. Yes, he really was behind a lot of the fundamental ideas for manifold. And I always like to say, without him, we would not have GPS on our phones, because GPS on our phones needs general relativity. General relativity is appropriately needs the language of manifolds, and manifolds came from Riemann.
Yep. Yep. So, yeah, I remember you always say Riemannian integral last year. Because you're so used to talking about Riemannian, like manifold and stuff. It's Riemann integral. He got it right this year, so thank you, Dr. Briggs.
Good job.
Okay, so lots of fun to be had with the integral, and we, as we said, we're not going to get terribly far, but we will establish some of the main ideas and definitely get a solid definition. And that will be our second last theme. For our last theme, we'll dig a little bit into series.
Exciting.
Yes, which of course are closely related to sequences.
Yes.
I mean, you can think about them as just special kinds of sequences,
yeah.
but they are incredibly special.
Yes.
And there is so much that we can do with series, and so much work that goes into series that it's almost a field unto itself.
Yeah. Have any of our students encountered series before?
Well, they would have
Taylor
done like
series?
a geometric series
Yeah.
in
Yeah.
high school, maybe.
Yeah.
Definitely in physics, they would have done some series, I think.
Yeah.
Yes.
In 1, 2, 4, isn't there?
Oh,
Taylor?
we do. Yeah, in 1, 2, 4, we
Yeah.
do Taylor polynomials,
Yeah. Yeah.
which are basically just the finite first little bits of Taylor series.
Series.
Yes.
That's
Which
that's
are
also
probably
beautiful.
one of the most important examples of series.
Yeah.
Yeah, and fundamental to analysis.
Yes.
Yes.
Very useful. Very useful. How many times do you use Taylor series to make your life easier?
Analytic function.
Analytic function. So yeah, very
Okay.
fun.
Well, I think we're slowly heading towards the end. But Professor van der Walt, before we finish, can you maybe tell us a little bit about your research?
I'd be happy to. So I'm an analyst, which means I do things that are similar to what you're doing in 220 now. At the moment, I'm very much interested in spaces of continuous functions, but not on intervals in the real line, on very general, it's called topological spaces. And the thing I'm thinking about very hard at the moment is about the duals of these spaces. So what this means...
Yeah, what is a dual?
What is
yes,
a dual?
well, so a dual consists of linear functionals. Now, for spaces of continuous functions, you can basically think of a linear functional as some kind of integral.
Okay.
And in fact, you can make that analogy precise. Right? So, like when you integrate a continuous function on 0, 1, it spits out a number. This is a functional. So a functional takes a continuous function in the kind of things I'm looking at the moment and spits out some number.
Okay.
Right? And I'm very interested in these things at the moment
Okay.
and the general structure behind them.
Beautiful stuff.
Yeah, wonderful.
Anything else exciting happen to share?
Anything else? Oh yeah, we covered some derivatives in the workshop. I'm planning to maybe upload some of our notes to Padlet, so be on
Okay.
the lookout for that. I have to do that over the break because
Yes.
there are other things to do at this point. But yeah, I will talk about, because we didn't have time to cover derivatives
Ah.
in the syllabus itself. So
Yes.
in the workshop, we just proved Taylor's theorem
Okay.
this week actually.
Cool.
Yeah.
Yeah, no.
And it uses boundedness property part 2.
Ha
Wow.
Strikes again.
Strikes again. Yeah.
Yeah, no, I think everybody is getting a little exhausted and
Yeah.
looking forward to having a
break.
bit of a break.
But we have to remind our students that after they come back from the break, they will have semester tests. So
I hope we don't have to remind them. I'm hoping that they are well aware of this fact by now. And that they will be making good use
yes,
of
so
this academic break.
they should not be too relaxed. I think.
Come on.
They should catch up on sleep
Yes, that's
and
important.
catch up on analysis.
Yes, exactly.
These are the priorities 1 and 2. Not necessarily in that order.
Oh my.
Oh dear.
Usually at the end of the chart, students already fall asleep, and when they heard that you said, "Oh, something test coming on," then they wake up again.
That's why I put it at the end.
Time to get going.
Yeah.
Okay.
Okay.
Well, that's it for this episode of Analysis Chat. Professor van Walt, thank you for joining us.
It was my pleasure.
Always great to have another perspective. And then, well, until next time. Cheers.
Cheers.
Bye bye.
Goodbye.